Okay, hello everybody. We are going to go ahead and just briefly review CASEL Unit 6, which mostly covered quantitative volt and amp measurements, that is, the electric pressure and charge flow. It also covered a little bit of Ohm's law. There's going to be a quiz on that this Friday, that's April 24th, that will cover this first half or so of Unit 6. That's right, there is actually more to Unit 6 after this. Okay, let's go ahead and get started. So first, I want to briefly go over the instructional goals of this unit. Okay, the first goal of this unit was regarding voltmeters and measuring voltage. What a voltmeter does is it measures the electric pressure difference. In order to do this, it must be connected in parallel and it must have a high resistance, and we'll go over that in more detail in a second. I also want to cover Kirchhoff's voltage law, or loop rule as it's sometimes called. The second thing that we covered with this unit was on ammeters, which measure current or the flow rate of charge. And in order to do that, those have a very low resistance and must be connected in series. And again, I'll be going over that briefly in a moment too. That's going to end up segueing into Kirchhoff's current law or node rule, which tells us about how current behaves. And then finally, we will talk about Ohm's law and how we can use it. Okay, so first on voltmeters. What does the voltmeter try to measure? Well, it's measuring the electric pressure difference between 2 points. That is, it is measuring the difference from this point to this point, or more specifically from here to here, which is pretty much the same thing. What it is not measuring, it is not measuring the electric pressure in this wire. It is also not measuring the electric pressure in that wire. It is measuring the difference, how much higher it is here compared to here. Now, in order to do that, it must be connected in parallel. That's because technically the voltmeter can only measure the pressure difference across itself, from here to here. It doesn't officially measure the difference from here to here. It measures the difference across itself. And so in order to tell me the difference across this light bulb, I have to make it so that the pressure difference is the same across the bulb as it is across the voltmeter. And as we know about things in parallel, if we connect two things in parallel, then they are going to have the same pressure difference. In this case, that is from red to blue. Now, in order to do that well, it does have to have a high resistance. Even if it had a low resistance, it is true that the pressure difference would still be the same. But a good measurement tool doesn't affect the circuit that it's measuring at all. If it had a low resistance, right, if it had a lower resistance than it does, then connecting it in parallel would let the charge go from here and through the voltmeter and back to the battery. But what we want it to do is actually to block the flow of charge that goes through it so that the current in this wire stays the same. Okay, so it can't let any charge through. If it did have a low resistance, then connecting it in parallel would let the charge move through it. But since it has a very, very high resistance, no charge can move through it, and we can consider it to be a good measuring tool because it doesn't change the rest of the circuit. When we did the activity with the voltmeter, we didn't explicitly talk about Kirchhoff's loop rule or voltage law, but we did actually talk about some of the points that should be hit in that law. In English, officially, the law reads that the sum of the voltage rise and voltage drop around a loop must be 0. And what that means is that so we can have any loop in a circuit like this one right here, which we've called loop 1, or this one here, which they've called loop 2, or even this loop here. Any completed loop, the voltage drop and the voltage rise has to come to 0. In the case of loop 1, that's relatively simple. If we had, say, a 9-volt battery here and both of these resistors are the same, then that means that it has to drop 4.5 on this resistor and another 4.5 drop here so that it can come all the way back to 0 by the time that it gets to the negative side of the battery, where it increases back to 9 and goes back around that loop again, 4.5 volts, 4.5 volts, up 9. If we did that with this loop here, it would be the same thing. We would still see 4.5 volts here, 4.5 volts here, and then back around here to 9. On loop 2, that's a little bit different because you notice that on loop 2, there is no battery. But on this resistor here, we're going backwards through it, so it's actually up 4.5 this direction, down 4.5 this direction, and it still has to sum to 0. So basically, in the case of loop 2, it's just saying that these two resistors in parallel have to have the same voltage across them, and that these two resistors in series have to add up to the voltage of the battery. Okay, the second thing that we learned about was ammeters. What does an ammeter try to measure? It measures the flow rate of charge from one point to another. In the case of this circuit that I have here, that flow rate that we want to measure is through the bulb, from here to here. From what we know about the way that charge flows, if we connect it in series, then the flow rate through the ammeter and the flow rate through that light bulb are going to be the same. Okay, so we have to put it in series so that the amount of charge flow through the ammeter is the same as the amount of charge flow through the light bulb. Now, technically, the ammeter, not the voltmeter, sorry about that, measures the charge flow rate through itself. Again, as long as it's in series, those charge flow rates should be the same. In order to do that well, it must have a very low resistance. If it has a very, very low resistance like the wire, then we could color code it like this, and the ammeter did not really have an effect on the circuit that we're measuring. It's just measuring the current that's going through that without changing the electric pressure anywhere. But if it did have a resistance, okay, if it did have a resistance, then our circuit would be color-coded maybe something like this. Okay, if it had the same resistance as this bulb or any other amount, that would be affecting the amount of charge that goes through that light bulb, as well as affecting the electric pressure in the circuit. Okay, so that ammeter has to have a very low resistance, or it does change the amount of flow through the circuit, and it also changes the electric pressure in the circuit, so we can't have that either. Okay, this brings us briefly to Kirchhoff's node rule, or his current law, which says that the sum of the currents going in and out of a node, where this type of point is a node, a connection point between wires, must be 0. If you select a point in the circuit, okay, such as this node here, but you could also do it just fine with that point there. If you select a point, the charge that flows into this point has to be the same as the charge that flows out of that point. In the case of this circuit, where we have 3 amps going in here and 2 amps going out here, that means that the remainder of this charge must be going up through here, so this I3 must be 1 amp. Finally, we have Ohm's law. In English, Ohm's law says that the current that goes through a resistor, okay, so if I have a resistor here, it says that the current that goes through that resistor, which we'll call I, is directly proportional to the voltage across that resistor. Okay, so we'll call this the voltage, and inversely proportional to its resistance, where this resistor has some resistance value R. Mathematically, that would be I equals V over R, or more commonly you'll see it written as V equals IR, that is, the voltage is equal to the current times the resistance of that resistor. That's a very simple algebraic model that shows the proportionality between voltage, current, and resistance. Now we can use that for an individual resistor, and that's usually how we use it, but it can apply to the whole circuit. At the point that we're at right now, we're only going to use that equation to solve for the equivalent resistance or the total resistance of a circuit. So I'll rearrange it so that it looks like this, where we are solving for our equivalent or total resistance for the circuit by dividing the total voltage of the circuit by the total current that goes through that circuit. Again, the equivalent resistance, that's just the combined resistance of the whole circuit. Adding resistors in series makes the equivalent resistance increase. Okay, if I put resistors next to each other in the circuit, that makes them increase. But remember that if I add resistors in parallel, it's going to make the equivalent resistance decrease, because it's going to make the total current increase. And if we make the bottom of that fraction get bigger, then the number for the resistance will decrease. Total voltage is usually going to refer to the voltage of the battery, and the total current is usually referring to the current that goes through the battery, which is going to be equal to the sum of the current through each branch. Okay, I'm about out of time here, so I'm actually going to stop it there. I believe that that's all for me. The next video will be me just going over the worksheet. Okay, have a good day, guys.